Alright, so let's do part B using the divergence theorem, meaning instead of computing this directly, we're going to take a look at this right here. So we will need the divergence of the vector field. And so given the vector field itself, the divergence, remember, is going to give you a scalar. So we differentiate this x with respect to x and get 1, plus we differentiate y with respect to y and get 1, plus we differentiate z squared with respect to z and get 2z. So in the end, we get 2 plus 2z for the divergence. We are going to need this capital E here. So that's going to be the three-dimensional region, which has as the surface this top circle, the bottom circle, and then the label around the side. So remember, this S is a closed surface, and S itself is the hollow can. E is if you filled the inside of the can with Play-Doh. If we were to draw a picture, E itself, hovering 2 units above, is this solid can, right? This thing is heavy. It's completely filled in on the inside. Okay, so then let's, yeah, so the rate goes from z is 2 to z is 8. And then the furthest out it goes here to here is, well, 3, yeah, due to the values of 9s that we see right there. Okay, so then the double integral over the surface of f dot d bolded s is just another way to write this right here, yeah, is due to the divergence theorem, the triple integral over the solid three-dimensional region E of the divergence of f, which we had just computed, was 2 plus 2z. We'll just copy that from right here into place, dv. Okay, now based on the shape, I hope your thought is to use cylindrical coordinates for this triple integral, right? So leave just a little bit of space between these. We'll write down here this 2 plus 2z, nothing to replace with the z because z itself is a cylindrical coordinate. And then remember that the dv would get replaced with r dz dr d theta. Please don't forget about this r right here. Z then, the innermost integral we see from the picture, should go from 2 to 8. The r integral goes from 0 to 3, and the theta integral from 0 to 2 pi. All right, well, due to how the integrand here is, we can actually, split things up multiplicatively. And have, there's first of all the integral, say from 0 to 2. You can only do this when you have multiplications, and you do have 2 plus 2z, that thing e times z times, I guess, a 1, right? So you have here one of the integrals is the integral from 0 to 2 pi of just 1 d theta, right? Like there's no thetas being mentioned. There's also then for the r integral, because it's all in factors, we can have integral 0 to 3 of r dr, and then we have the integral from 2 to 8 of 2 plus, let's just factor out a 2 here, so 2 times the integral from 2 to 8 of 1 plus z dz. All right, and so then, okay, that first integral here is going to be 2 pi. Yeah, the next integral is going to be, well, r squared over 2. Plug in 3, then plug in 0. So the plug in of 0, that part's going to simplify to 0, fortunately for us. That doesn't always happen. So we'll just end up with 3 squared over 2 for that. Okay, this next integral we'll have, let's just copy the 2, and then we have to integrate 1 plus z, which will be z plus z squared over 2. Yeah? So if you want off to the side here, the integral of 1 plus z dz is z plus z squared over 2 plus c. So based on that, we have here 8 plus, let's do this. Let's use some more parentheses. 8 plus 8 squared over 2 minus 2 plus 2 squared over 2. Is that the right number of parentheses? I think so. We'll cancel the 2 here on top and bottom. And let's see, the 3 squared times 2 we'll have there equals 18 pi. that takes care up to right there. If we work out what we have inside parentheses here, we'll have 8 for that. 64 over 2 is 32. Minus, and then let's work this out right here. So 2 squared over 2. So that's a 2. 2 plus 2, 4. Okay, there we go. All right, so this is 18 times pi times, and then what's in parentheses ends up being 36, and that ends up being 648 pi, and that number matches the number that was computed right up there. Yeah, so these, in fact, match the way they should. So, just some comments here. The moral, the takeaway message here is that after converting to a triple integral using the divergence theorem, it's sometimes helpful to switch to cylindrical or to spherical coordinates, right? And how do you know? Well, there's never one right way to do it, I guess. This just depends on the shape, depending on the shape of E. So take a look at the shape we had here. Yeah. Don't always do things as a dz, dy, dx. Don't always do things in cylindrical, and don't always do things in spherical coordinates. Look at the shape and think about what is the nicest way to do things, right? For an interactive question, I'd like you to focus less on this matter right now, and instead just on the two ways that we did this. So there was a part A, and there was a directly, and there was a part B. And so regarding that, I'd like you to really take a moment to think about what's going on. Interactive question, comment on which was the easier way to get that the flux was 648 pi. Now, in your opinion, so hopefully in your opinion one way was easier than the other, but in your opinion, what made the easier way easier? So you should, I hope, have an opinion that one way was easier than another, but I want you to think about it. I want you to put some words to it. What really made the easier way the easier way?